trying to keep up with AI, it really feels like trying to outrun a rocket sometimes, doesn't it?
Absolutely.
Especially when you start digging into the actual infrastructure, the nuts and bolts making it all work.
Right.
So think of this deep dive as your maybe cheat code,
Yeah.
the quick route to understanding what really matters for AI performance, specifically AI inference performance.
Exactly. Today, we're really getting into the IT leader's guide to AI inference and performance. We're basically pulling out the mission-critical stuff for any of you leading AI deployments.
Precisely. You've given us a good pile of material, articles, research, your own notes, and our mission really is to boil that down. Get to the actionable insights. We want to help you optimize that inference setup, tackle the costs, and ultimately give your users a better experience.
And inference, that's really where the rubber meets the road for AI models, isn't it?
Yeah, taking them from theory to practice.
Right. This is AI writing code, summarizing huge documents, making images, videos in real time. Inference is the engine for, well, actual automation, new business models.
It's genuinely transformative stuff, but like any powerful tool, there's complexity.
Always.
And a big part here is managing the costs, right?
Right.
Especially when you scale these inference workloads up.
Yeah, those costs can ramp up fast.
All while making sure performance, that responsiveness, the latency doesn't just, fall off a cliff.
And the guide really zeroes in on that exact problem.
Yeah.
How do you tune AI performance so inference costs are manageable, but without wrecking scalability or that crucial user experience? It's definitely a balancing act.
Okay, let's unpack that a bit.
Yeah.
The guide points to two main things driving inference costs.
Yeah.
First, the platform's capability. It's throughput, how many requests it can handle.
Right. And tied right into that is the cost per output, cost per token the AI generates. It's not just raw speed, it's efficient speed.
But it's tricky because just chasing higher throughput can actually backfire, can't it? If it slows down the response for a single user.
That's a huge point. Latency. The guide really stresses time to first token TTFT. That's the wait before the first bit of the answer appears.
Okay, that initial hello.
Exactly. And then there's time per output token TPOT, how fast the rest of the answer comes out.
And you can't just optimize one in isolation, right? The guide suggests there's often a push-pull. Boost throughput, maybe TTFT suffers.
That's the tension. So how do you measure the real effectiveness? This brings up a key question for you, the listener.
Right. How do you know if it's actually working well?
The guide introduces this great metric, Goodput. It's not just volume, it's how many requests you can handle while keeping both TTFT and TPOT within limits that work for your users.
Ah, so it's a more holistic view.
Much more. So the key insight here for you is look beyond just raw throughput. Focus on Goodput. Are you delivering a good experience at scale? That's the metric with real business impact.
That makes a lot of sense. It's about quality under load. Now, the guide also mentioned another cost factor, maybe less obvious.
Yeah, the second big one is time to market.
Ah, right.
I mean, AI is moving at warp speed. If your inference software setup is a nightmare, unreliable, badly documented, no support, you're just going to hit delays, costly delays.
And getting those AI features out fast is a huge edge.
Absolutely. Wasted time wrestling with a clunky system just eats profit.
Okay, so we get the why and the cost drivers. The guide then uses some real-world examples. Wealthsimple first. Tell us about that.
Yeah, Wealthsimple, big Canadian investment manager, over $50 billion AUM. They needed a better way to deploy their ML models, for client services.
And they were hitting walls. Their old platform wasn't cutting it.
It wasn't standardized. They said it took months sometimes to deploy a new model.
Months. Wow, that would really stifle innovation. So what do they do?
They switched to NVIDIA's AI Inference platform. And the results, according to the guide, were pretty stunning. Well, in just the past year, they rolled out over 30 AI models, powered 145 million predictions.
145 million, okay.
Right.
And that deployment time problem.
Went from months to under 15 minutes.
15 minutes.
Yeah.
That's incredible. A total game changer for iterating.
Absolutely. And the platform stability seems to have been amazing, too.
No IT tickets for AI inference in 18 months. That says a lot about reliability.
It really does. And it wasn't just speed. NVIDIA's Triton inference server helped them boost those personalized ML services, fraud detection, transaction optimization.
So better, faster financial experiences for clients.
Exactly. Plus, a huge jump in uptime, from 95% to 99.999%. 5 nines.
For financial stuff, that kind of reliability is non-negotiable.
You got it. And they're running this on NVIDIA accelerated compute in the cloud using NVIDIA AI Enterprise for security and stability. It's a really clear example of how the right inference platform transforms things.
Okay, great case study. So we see the benefits. Now the guide shifts focus a bit, emphasizing that different AI apps need different things from the infrastructure. It's not one size fits all.
Definitely not. And what's really key for you, the listener, is you can't just pick hardware based on one benchmark number and expect it to work great for everything.
Right. Different use cases stress the system differently.
Exactly. Chatbots versus, say, document summarization tools. They have very different demands on compute. They need different software optimization. And that directly hits your TCO, your total cost, and how interactive it feels for the user.
Okay, let's take the chatbot example. What should IT leaders focus on there?
For those LLM chatbots in e-commerce, customer service,
Yeah.
responsiveness is king. Users want answers fast.
So that time to first token, TTFT, has to be really low.
Crucial. To keep users engaged, stop them leaving. The speed of the rest of the answer, the TPOT, is maybe less critical as long as it feels natural, close to reading speed.
And chatbots often handle lots of users at once, big batch sizes.
Typically, yeah. Large user bases often mean you can batch requests effectively.
Okay, quick start, steady flow. How does that compare to, say, document summarization?
Summarization is pretty different. Think summarizing a long research paper, a big report. The input can be massive pages, hundreds of pages.
So the priority shifts.
Yeah, here you want the complete summary generated quickly. So fast time per output token, TPOT, is the focus. Ideally faster than a human could read the original.
And users might tolerate a slightly longer initial wait?
Generally, yes. And because the inputs are so large, batch sizes tend to be smaller. You need smart software to keep throughput high with those smaller batches.
So speed of completion wins out there. What about question answering bots? Where do they fit?
Q&A bots. They need that quick initial response like chatbots because the user query is usually short.
But the process is different.
Often, yes. They frequently use something called retrieval augmented generation, RD.
ROG.
Think of it as the AI looking stuff up in a knowledge base before answering. So, even with a short question, the AI pulls in relevant info, making the actual inference request much longer internally.
Ah, so more going on behind the curtains. What does that mean for infrastructure?
It means you need a system that handles long input sequences efficiently, but still delivers reasonably fast output.
Right.
And because that knowledge base often lives in CPU memory,
Yeah.
having really fast connections between the CPU and GPU faster than standard PCIe becomes important. Something like NVLink.
NVLink, that super fast GPU highway from NVIDIA.
Exactly. It helps move that knowledge base data quickly, boosting performance, lowering costs. Crucial when you're splitting big models across GPUs.
Got it. Fast data movement is key. Now, the guide also talks about AI agents. The next step. What are they and what do they demand?
AI agents. Yeah, they're a whole other level, not just single interactions. They tackle complex multi-step problems, reasoning, planning.
Sounds sophisticated.
They ingest tons of data, analyze, strategize, execute tasks. They can even learn from feedback loops.
Whoa. So what does that mean for inference?
It means they often use function calling, triggering other tools. They orchestrate multiple AI models. All this generates more tokens per session.
So more complex processing.
Right. So if you're looking at agents, the guide says picking an inference platform with good abstraction tools for managing all these moving parts. That's critical for performance.
Orchestration and coordination become paramount. Okay. Given all these different use cases, the guide really hammers home the importance of benchmarking. But not just any benchmark.
No, absolutely not. The advice is strong. Your benchmarks need to closely mirror your actual production use case
Why is that so critical?
to make sure you can meet your SLAs, your service promises to users, and to avoid nasty surprises with infrastructure costs because you underestimated what your specific app actually needed.
Tailor the testing to the real world. Makes sense.
Yeah.
Speaking of real world, another customer story, Perplexity AI. They handled insane query volumes, right?
Insane is right. 435 million queries a month, and each query might trigger multiple inference requests.
Wow. How do they manage that scale and keep costs down?
They're using a combination: NVIDIA H100 GPUs, Triton Inference Server, and TensorRT-LLM.
A powerful stack. What are they running on it?
Over 20 different AI models simultaneously, including various Llama 3.1 versions. Plus, they use smaller classifier models to route requests smartly to the right big model.
Clever. And it's all running on Kubernetes.
Yep, gives them that scalability to handle traffic spikes and still meet their SLAs.
So how are they optimizing performance at that scale? What's the secret sauce?
A lot of it comes down to smart scheduling and batching using Triton. They're constantly tuning algorithms to minimize that intertoken latency,
Yeah.
especially for the user-facing stuff.
Trying to make it feel instant.
Exactly. Lots of A/B testing different configurations too, squeezing the most out of the GPUs while hitting performance targets.
And doing this internally on NVIDIA GPUs saves them money.
That's a key takeaway for listeners, yes. Deploying internally like this brings substantial cost savings versus other routes. They distribute models smartly across GPUs, use TensorRT-LLM optimizations. It's all about lowest cost per inference while meeting those strict SLAs.
Very impressive. Okay, let's broaden out from specific examples. The guide talks about general deployment factors impacting inference. What are the big areas IT leaders need to think about?
The guide breaks it down into 5 main areas. First, the hardware architecture. Second, the model size itself. Third, maximizing your hardware use with model concurrency. Fourth, handling models with multiple data types modalities. And fifth, using advanced batching techniques.
Okay, 5 key areas. And the goal isn't necessarily to become a deployment expert overnight.
No, not at all. It's about giving you, the IT leader, the framework to understand how these things interact so you can make informed design decisions for your specific needs.
Right. Let's start with hardware architecture. What's important beyond just the raw chip stacks?
Well, the guide makes a great point. Just looking at peak FOPS or memory doesn't tell the whole story. The efficiency of the entire software stack, drivers, libraries, the inference server is absolutely critical for the real-world performance you actually get.
That makes sense. And cost isn't just a sticker price.
No, it's not the GPU price or the hourly cloud cost alone. The real metric is performance per watt or performance per dollar. A pricier GPU that's way more efficient might actually save you money long term.
Especially with data center power limits and energy efficiency being such big concerns now.
Huge concerns. Maximizing inference throughput within your power budget is key, and the guide notes how NVIDIA GPUs have really driven parallel processing, offering big jumps in performance per watt and per dollar compared to CPUs for these workloads.
And they keep pushing that envelope. The Blackwell architecture is highlighted as a major leap.
A massive leap, up to 30 times faster inference for those huge trillion-parameter models compared to the previous generation.
30 times.
Advancements like a second-gen transformer engine, faster NVLA-NK interconnects. Remember NVLink, that GPU superhighway? It's even faster now.
The guide mentions the Blackwell GPU has 208 billion transistors.
Yeah.
Because it sounds immense. And new tech like the second-gen transformer engine, FP4 AI. What do these mean practically?
Okay, so the new transformer engine plus the custom Blackwell Tensor cores and TensorRT-LLM software. They're all tuned to speed up inference for large language models, especially those mixture of experts models. The new precisions help accuracy and throughput.
And FP4 AI.
That's about efficiency. It basically doubles performance, doubles memory bandwidth, and lets you fit double the model size onto one GPU compared to the previous FP8 standard. Huge efficiency gain. More bang for your buck, essentially.
Wow. Okay, but it's not just the GPU. It's how it pairs with the CPU. The guide mentions the NVIDIA GB200 Grace Blackwell superchip. What's special there?
The GB200 superchip tightly links 2 Blackwell GPUs with an NVIDIA Grace CPU using an ultra-fast interconnect called NVLink C2C. 900 gigabytes per second, bidirectional, just between those 2 GPUs. That kind of speed is vital for handling the massive data flow in these big AI models.
And the Grace CPU itself is built for AI. 72 ARM cores, high bandwidth fabric.
Exactly. Grace is designed for high performance and energy efficiency. Its fabric has double the bandwidth of traditional server CPUs. Plus, it's the first data center CPU using fast LPDDR8 5x memory with error correction. Massive bandwidth, way less power, like a fifth of traditional DDR, all about performance per watt.
So a power-efficient brain matched with those beastly GPUs. Now, for the truly enormous models, one GPU isn't enough. You need multiple GPUs working together. How does NVIDIA handle that?
Right. For exascale computing and trillion-parameter models, you need seamless, super-fast GPU to GPU communication. The guide points to the NVIDIA GB200 NVL72.
NVL72. What is that?
It's a full rack system. It connects 36 of those GB200 superchips, that's 72 Blackwell GPUs total, into one giant liquid-cooled NVLink domain. It basically acts like one massive unified GPU.
72 GPUs acting as one. That's staggering compute power. What connects them?
5th generation NVLink. Doubles the speed again, 100 gigabytes per second per link. Plus the NVLink switch tech. Inside that NVL72 rack, you get 130 terabytes per second of total GPU bandwidth. Unprecedented scale for distributing huge model computations.
And the performance uplift for massive models.
The guide quotes up to 30x inference speedup, 25x lower TCO, and 25x less energy compared to the prior generation, using the same number of GPUs for something like a GPT MOE 1.8T model. Transformative efficiency gains at the high end.
Truly mind-blowing numbers. Okay, let's shift gears to another key factor, model size. How does the number of parameters affect inference?
Well, generally, bigger models, more parameters, they tend to give better, more nuanced answers, but they also demand a lot more compute power to generate each token. It's a direct trade-off.
So developers release different sizes, like the Llama 3.1 family, 8 billion, 70 billion, 405 billion parameters.
Exactly. It caters to different needs. If you need top accuracy for complex tasks, maybe you need the giant model. But if speed is critical or your budget or hardware is limited, a smaller version might be the smarter, more cost-effective pick.
Makes sense. Choose the right tool for the job. Now, with these super powerful GPUs, they might be sitting idle with smaller models. That's where model concurrency comes in.
Precisely. You want to keep those expensive GPUs busy. Model concurrency is about running multiple models or multiple copies of the same model simultaneously on one GPU or across several GPUs. Especially useful for smaller models.
And the benefits are?
Higher overall system throughput, potentially lower latency for users, and better use of your existing hardware. No need to buy more GPUs if you can use the ones you have more effectively. Lowers your TCO.
And NVIDIA Triton makes this easy.
The guide says Triton simplifies it a lot, often just setting a flag in the config. You tell it how many instances, on which GPUs. Triton can even act like a smart traffic cop, loading and unloading models dynamically based on demand if you have more models than fit in memory at once.
Smart resource management. What about models handling images or audio, not just text? Multiple modalities.
Right, multimodal models understand different data types. This makes inference trickier. You need to process inputs and generate outputs across these different modalities efficiently.
And the NVIDIA platform has specific help for that.
Yeah, the guide mentions optimized encoders for audio-image input using TensorRT and optimized text decoders using TensorRT-LLM. Triton then manages deploying these with features for handling multiple images in one go or reusing KV cache smartly across inputs to cut latency.
So specialized optimizations for diverse data. Okay, another big area for performance. Batching requests. We touched on this with Perplexity. What are the advanced techniques?
Right. GPUs love parallel work, so batching requests is fundamental, but it's that balancing act. Batch size versus throughput versus latency.
Bigger batches, more throughput, but higher latency.
Generally, yes. Small batches, low latency, but might underuse the GPU. The NVIDIA platform offers sophisticated ways to manage this, like dynamic batching.
How does dynamic batching work?
The system waits just a little bit based on rules like batch size or time limits, hoping more requests arrive to make a bigger, more efficient batch. It can lower your cost per token without users really noticing much extra delay.
Clever. And for sequential stuff like video frames, sequence batching.
Correct. Ensures related requests, like video frames, get processed in order on the same instance, maintaining the model's state correctly. Crucial for coherent output.
And in-flight batching sounds even faster.
It is. That's a TensorRT-LLM feature. It starts processing requests as soon as they're ready, without waiting for a full batch to form. Lets new requests start while others are still finishing in the batch. Boosts speed and throughput.
Keeps the pipeline constantly full and moving. So these advanced batching methods are key to finding that throughput latency sweet spot. Now, what happens when models get so big they don't fit on one GPU? Parallelization becomes necessary.
Absolutely essential for the monster models. The guide outlines several methods IT leaders need to understand. Let's start with data parallelism, DP.
Okay, data parallelism.
This is the simplest. You just copy the entire model onto multiple GPUs. Each GPU handles different user requests independently. No communication needed between them for a single request.
So more GPUs means you handle more users. Scales linearly for volume.
Exactly. It's great for scaling user volume, but the guide notes for the really huge LLMs, the model itself is too big for one GPU's memory, so DP alone isn't enough. It's often combined with other techniques. So key takeaway for you, the listener, DP scales users.
Got it. What about tensor parallelism, TP? How's that different?
TP is fundamentally different. Instead of copying the whole model, you split the model's parameters across multiple GPUs. A single user request is then processed across all those GPUs simultaneously.
So the GPUs work together on one request.
Right. They combine the results over the network. This can really speed up the processing time for a single user, improving interactivity, especially for big transformer models.
So TP helps make it feel faster for the user. Any downsides?
Well, if you scale TP to too many GPUs without a super fast interconnect, like NVLink, the communication overhead between GPUs can actually slow down overall throughput. So for making big models feel fast, TP and expert parallelism are critical, but you need that fast interconnect.
Makes sense. Lots of chatter between GPUs. Next is pipeline parallelism. PP.
PP divides the model layers sequentially across different GPUs. A request flows through the GPUs one after another like an assembly line. Each GPU handles its assigned layers.
Useful for spreading out large model weights.
Primarily, yes. But the guide suggests it might not be the most efficient for throughput, and because it's sequential, it doesn't usually boost user interactivity much. Each request has to go through step by step.
Okay. Lastly, expert parallelism, EP. Sounds specialized.
It is. Used for those mixture of experts, Mayo models, these have multiple expert subnetworks. For each request, the system routes it to only a subset of these experts.
So each request uses fewer parameters.
Exactly. Reduces the computation needed, optimizes processing, but it relies on high bandwidth GPU communication.
And the performance impact.
Can significantly boost throughput, especially combined with other methods. And importantly, well-configured EP can often maintain or improve user interactivity without big throughput trade-offs.
It sounds like the real magic is combining these methods.
Absolutely. The guide stresses that strategically combining DP, TP, PP, and EP is how you really optimize performance for huge models on multiple GPUs. You minimize that throughput versus interactivity tension.
Then give example.
Yeah, with a GPT 1.8T MoE model, shows how different combos yield different balances. Like adding expert parallelism to pipeline parallelism significantly boosts interactivity with little throughput loss. Or adding tensor parallelism to an expert pipeline boosts throughput while keeping interactivity high.
So it's a complex configuration game, crucial for IT leaders managing these big deployments to understand those trade-offs.
Precisely. Well-planned setups can deliver both high performance and responsive experiences. It's not always an either. These techniques are critical as models keep growing.
Okay, hardware, models, parallelization, covered. Now, the cloud's role. Huge enabler for AI inference.
Massive. Cloud is transformative. Scalability, cost efficiency, access. AI inference is following the path of other workloads moving to the cloud. Industry forecasts show cloud-accelerated compute as the fastest-growing segment for enterprise AI inference.
Makes total sense. The flexibility seems perfect for AI's fluctuating demands.
Exactly. And for you IT leaders, it's a big opportunity. Combine powerful cloud instances with optimized AI software, you can get better performance without costs spiraling.
But it's not just any cloud instance. The guide mentions meeting flexibility in choosing GPU types.
That's really critical. You need the agility to pick the right GPU from the cloud provider's menu for each specific AI workload. Over-provisioning wastes money. Under-provisioning kills performance.
And integration with existing cloud tools is important too. Avoid retraining teams.
Hugely important. Pick an inference stack that plays nice with the MLOps tools your teams already use. Minimizes friction, lets them focus on optimizing inference, not fighting integrations.
And choosing platforms available across multiple clouds helps avoid vendor lock-in. Smart move long-term.
Definitely. Gives you leverage, deployment flexibility, freedom to choose the best cloud platform per application, considering both tech needs and cost.
And NVIDIA is highlighted for being available across all major clouds.
Yes, their latest GPUs power instances everywhere, wide choice of performance and cost. And crucially, their whole AI inference stack, Triton, the NI microservices, integrates fully with the big cloud MLOps platforms.
Like AWS SageMaker, Google Vertex AI, Azure ML, OCI. And deployment is easier with low-code options or pre-configured images.
Right, these streamlines getting started. Get workloads running fast without tons of manual setup, saves time, cuts operational costs, makes scaling inference in the cloud much more efficient and less complex.
Let's make this real again, another case study. Amdocs. What did they achieve using the cloud?
Amdocs, big provider for communications and media companies, they built Amaz, a telco-specific generative AI platform. They used NVIDIA NIM inference microservices on NVIDIA DGX Cloud to deploy fine-tuned LLMs for things like customer care and sales.
And they fine-tune the models themselves.
Yep, using curated, anonymized telco data. Fine-tune models like Llama and Mixtral using efficient techniques like LoRa, and the results using NIM were significant.
How significant?
80% lower latency.
Yeah.
30% better accuracy. And get this, 40% fewer tokens consumed.
40% fewer tokens. That directly cuts costs.
Huge impact on performance and the bottom line. Shows how optimized microservices in a powerful cloud setup can dramatically improve LLM performance and reduce costs for specialized industry applications.
Now, a common headache. Dealing with unpredictable user demand. Provisioning for peak load is wasteful. Kubernetes is the answer here.
That's the recommendation. Forecasting AI demand is tough. Over-provisioning is inefficient. Kubernetes lets you scale, dynamically add or remove resources like GPUs automatically based on real-time demand.
So scale up for busy times, scale down when it's quiet. Much more cost-effective.
Exactly. Cost-optimized, performance-efficient infrastructure management. And the NVIDIA AI platform Triton and NVIDIA fully supports Kubernetes integration.
How does that scaling actually work with Kubernetes and NVIDIA?
Okay, so as requests increase, Triton metrics like queue lengths get monitored by tools like Prometheus. This data feeds the Kubernetes Horizontal Pod Autoscaler, HPA. Based on those metrics, the HPA automatically spins up more pods containers running your inference service, each with GPU access to handle the load. A key metric mentioned is Triton's queue-to-compute ratio, a direct indicator of responsiveness for the HPA.
So the system self-adjusts. Smart. Keeps performance high, cost-controlled. Powerful stuff. Okay, next topic. Streamlining complex AI pipelines with model ensembles. What's the idea?
The reality is many AI apps aren't just one model, they're pipelines. Pre-process data, run one or more models, post-process the output. An ensemble integrates all these steps models pre-post processing into one unified pipeline for better efficiency.
Like the example of generating marketing images with SDXL. Maybe zoom in, generate, then upscale.
Exactly. Putting those steps together streamlines data flow, cuts latency between stages, and optimizes resource use overall.
And Triton helps manage these ensembles, orchestrates them.
Absolutely. Triton's Model Ensembles feature automates managing these multi-step pipelines. No need to hand code the connections between steps. Reduces complexity, errors. It can even run pre-post processing on the CPU while the main model runs on the GPU flexible resource allocation.
So it simplifies building and running these more complex apps. Key benefits.
Reduced end-to-end latency, better resource use, less network overhead since data stays local, and easier integration of diverse models and processing steps, sometimes even no code.
Sounds very efficient. The practical example was text-to-image generation.
Yeah. User types text, AI makes image. The pipeline might involve an LLM for the text, a diffusion model for the image, plus pre- and post-processing. Ensembles in Triton automate and optimize that whole workflow in one shot.
Streamlines the whole thing. Another customer example.
Sure.
Enhance using ensembles.
Yeah, let's enhance, an AI image enhancement startup. They've used Triton for years. Their new AI photo shoot product uses SDXL for e-commerce photos.
Yep.
They integrated SDXL smoothly into their existing complex pipelines, using Triton's ensemble features, framework support, and dynamic batching. Minimal ML engineering effort needed.
And they found cost savings, too, by switching GPUs.
They did. Careful analysis showed a 30% cost cut by moving SDXL workloads to NVIDIA L4 GPUs on Google Cloud G2 instances. And they plan to migrate more. Shows how the platform enables both innovation and cost optimization.
Great example. Okay, we've covered a lot of ground. The guide then goes into some really advanced inference techniques for orgs really focused on cost or pushing the performance edge.
Exactly. These are the cutting-edge optimizations from Triton and TensorRT-LLM. Things like chunk prefill, multi-block attention, KV cache early reuse, disaggregated serving, and speculative decoding. Tools for squeezing out every last drop of performance and efficiency.
Let's unpack those. Chunked prefill first. What's that?
Okay, LLM inference has two phases. Prefill, processing the input prompt, and decode, generating output tokens. Prefill can be heavy work. Chunked prefill breaks that prefill work into smaller chunks. It improves parallelism between prefill and decode, reducing bottlenecks, helps with long inputs, high concurrency, uses GPU memory and compute better. Decouples memory needs from input length too. TensorRT-LLM even handles chunk sizing dynamically.
So it makes that initial setup phase faster and more scalable. What about multi-block attention? Sounds like it tackles long context windows.
Precisely. Models now have huge context windows, like Llama 3.1's 128K tokens. That creates challenges for real-time speed. Multi-block attention in TensorRT-LLM smartly spreads the decoding work across all the GPU's processing units.
Boosts throughput. Avoids bottlenecks from giant KV caches.
Exactly, and keeps the GPU highly utilized even with small batch sizes, common in real-time apps.
And the performance game.
The guide mentions up to 3.5x more tokens per second on high-end NVIDIA hardware without hurting that critical time to first token.
Impressive. Next, KV cache early reuse. Why is reusing the KV cache so important?
Generating that KV cache takes serious compute power. Reusing parts of it speeds up token generation significantly.
Okay.
Traditional methods wait for the whole cache before reusing anything. KV cache early reuse is smarter. It starts reusing portions of the cache as soon as they're ready during generation.
So it accelerates things faster, especially for common prompts.
Yes, huge speed-up potential, especially with system prompts or repeated instructions, like in enterprise chatbots where the beginning of many conversations is the same. Can accelerate TTFT up to 5x in high demand, the guide says. Game-changing responsiveness.
Wow. Okay, disaggregated serving. Sounds like a bigger architectural change.
It is. Traditionally, prefill and decode run on the same GPU, but they have different resource needs that's inefficient. NVIDIA Triton disk serve separates them.
Decouples prefill and decode.
Yes. Lets you allocate resources independently for each phase. Maybe more GPUs for prefill to optimize TTFT, a different setup for decode to maximize TPOT. You can even use different parallelism types for each phase.
And this flexible allocation saves money.
Potentially cuts inference costs by up to 50%, the guide claims, while still hitting your performance SLOs.
50%, that's huge. Lastly, speculative decoding. Speeds up token generation how?
Standard generation is one token after another, autoregressive, can be slow. Speculative decoding tries to generate multiple possible token sequences in parallel.
Like guessing ahead.
Sort of. TensorRT-LLM uses advanced methods like draft target eagle decoding. If the speculated sequences are right, you get way more tokens per second overall.
Big boost to throughput and user experience without hurting quality.
Exactly. Very useful for low latency, high throughput needs. Guide mentions up to 3.5x more token sec for Llama 3.370B.
Multiple guesses verified. Very clever acceleration. These advanced techniques really show the depth of optimization available.
Absolutely. For orgs really pushing the limits, these unlock major performance gains and cost savings.
Well, this has been incredibly thorough, a real deep dive into AI inference performance.
It really has.
Yeah.
And it's clear the NVIDIA AI Inference platform aims to support organizations wherever they are on their AI journey.
Right. If you're just starting out, experimenting, focused on time to market, those foundational deployment strategies we covered are a great starting point.
But if inference cost is a major driver, if you're focused on gross margins, then those advanced techniques we just discussed offer powerful levers for maximizing efficiency and cutting expenses.
The end goal for everyone really is maximizing system efficiency, hitting top performance, and keeping costs manageable.
Couldn't agree more. And for listeners wanting to dig even deeper or get started, the guide points to the NVIDIA AI Inference Solutions resources online.
Good place to find info on NVIDIA NIM microservices for easy deployment, or Triton and TensorRT for more customization.
Exactly. Everything from prepackaged solutions to the tools for deep optimization.
Fantastic. Great resources. So to wrap up, here's maybe one final thought for our listeners to chew on. Considering how fast AI models are advancing and how fast these inference techniques are evolving, how do you see the role of the IT leader changing? In managing all this AI infrastructure, what new skills, what new expertise might be absolutely essential for success in this incredibly dynamic landscape just a few years down the road?
That is a fascinating and really crucial question to think about.
Definitely something to ponder. Thanks for joining us for this deep dive.